So Jamie's visiting City at the moment. Many of you might know him from around the Scala community. Does lots of good things. But tonight he's going to talk about JVM, memory model immutability. So thanks, Jamie.
Thank you. And thank you, Mark. And I just want to let you know I really appreciate that awesome talk about Akka he just gave. No, it was really funny because one of the things I was thinking about talking about was the marriage of purely functional programming and Akka at the boundary so that you have programming or programs that are both as correct as possible, which we all truly value, and have applications that are as robust as possible. So that was what I was going to talk about. Unfortunately, my coworker, Christopher Hunt, who has snuck out, he talked me into instead giving this talk about the Java memory model. And that was because it's something not a lot of people talk about. It's not something a lot of people think about. And therefore, it's something we should all be aware of when we're trying to write performant applications that are multi-threaded. And these days, we all are, right? So how many people have read the Java memory model? All right, we got a few. That's good. Yeah, and a few like that. Even if you looked at it just briefly, it is stultifying. It is. It's boring. But it's so important, right? So first off, who am I? My name is Jamie Allen. I've been working at TypeSafe for about 3.5 years. I've written the book, it's really small, called Effective Akka. Some might joke that's because it's the only effective ways it could be used. But no, I'm kidding when I say that. It's meant to be a book that's very easy and readable on like a mobile format. I'm also working on something called reactive design patterns. And reactive, of course, is this word that everybody's getting tired of. But finally, somebody put a definition to what a reactive application was, and therefore we can talk about it and use the word without it just being pure fluff. The Java memory model itself, we're going to talk about this, and then we're going to talk about what concurrent and parallelism mean. We're going to talk about how the Java heap works, and then how do we protect shared state on the heap, and how do we publish it across multiple threads. So when we talk about applications today, we're running on much more cores than we ever have before. Even our phones these days have 4 cores. And if we want to leverage this effectively, we've got to make sure that we're writing applications that are going to make sure all of those cores are doing work efficiently at all times. But that isn't easy. It, again, gets back to what Mark was talking about, isolation. You have to make sure that what you're doing is not impacting anything else, right? And when you do that, it's fantastic to be able to get all this stuff that's jamming through individual cores really quickly, just like individual boxes whenever you're doing things like MapReduce across HDFS and Hadoop ecosystem, all that stuff. But you still have problems. You got to split work apart. You got to join work back together, and that can be really expensive. So how are we going to do this without things like coordinated blocking, locking threads so that we're figuring out who can do what when? I was talking to Jed and his team here at Atlassian, and they were telling me all about how they'd managed to build pipelines of work that had no coordination points between any others. And this is heaven. If you have that kind of work, you have linear scalability where you could start up threads, you could start up nodes, and you can just fire work into them, and they've got no dependencies on anything else. And when you're there, then you've got applications that can perform extremely well. This gets back to something called Amdahl's law. How many people have heard of Amdahl's law? That's amazing. That's the most hands I've ever seen when I've asked that question. And the idea is that as you reduce the number of touch points in your application, the faster it can get. It's really the inverse of that. The more you add touch points into your application, the more you hurt the performance and parallelization that you get. So if you have no touch points, you have 100% parallelism efficiency. But if you have even 1% of touch points and coordination inside of your logic, you reduce your capacity for efficiency by 60%. You are now only 40% as efficient just because you had 1% of coordination in your application. This is a mathematical law. So then we start getting into things called the universal scalability law, where we're going to think about, I'm actually hurting performance as I parallelize or expand the footprint of the work I'm doing. Think of Cassandra or any kind of DynamoDB on the back end. The more it's got to gossip to figure out who knows what when, the more you're hurting performance. As you add nodes, that coordination, that gossip is going to get greater and greater. You're actually hurting performance by adding nodes as opposed to helping it. So the universal scalability law is like an addendum beyond Amdahl's law. So I want you to look at the JVM, and I want you to ignore sort of this left-hand area over here, the method area. That's pretty irrelevant. This is a diagram by somebody named Pablo Francesconi. I've never met him, but I really like the way it laid things out here. With the heap, talking about instances of classes, and threads with stacks and frames inside of those stacks that represent method calls, right? Every one of these areas is very important for what we're going to talk about here in the memory model. The JVM is a really fantastic piece of engineering. We make fun of it all the time, but you look at where Go is struggling right now. They're so excited about what they've done with their memory management, but in the end, they are going to realize that they need to have generational garbage collection that is multi-region if they ever want to reach true performance. It's inevitable. And it's been proven by the JVM and the work they've been doing in managing memory for the past 20-odd years. So watch them go through the throes of what Java did for the past 25 years. It's okay. They're going to learn just as we did. So there are two primary concepts inside the Java memory model. And one is this concept of happens before, right? That if I do something, I have a guarantee that it happens before something else. If A happens before B, A's result should be visible to B. So this is about if I have a thread executing and it does work, I have to make sure that another thread executing can see the changes it's making when it needs to, right? And then I have synchronized with. The idea that whenever I do something, I may have to push it all the way back to main memory to make sure that it's synchronized across all of the threads that may need to see this. Behind all these details are the low-level concepts of memory management and cache lines, right? You have cache lines, which represent the way data is spread across all of these places that it's put, like the individual caches, where it's L1, L2, L3, and all the way back to main memory. And they can be shared, which is even worse, because we talk about how much we want isolation. We talk about how much we want immutability. If you have mutable state sharing cache lines, you are going to run into performance issues regardless of how you structure your program, right? Immutability saves you from some of this. But even then, you've got cores who are sitting there and arbitrating via messages who can do what when, using a protocol called MESI plus F. Modified, exclusive, shared access, invalid because somebody's changing something on me, right? This is all message passing between cores, and it gets even worse when they go cross-socket. I could have an 18-core socket sitting there. That's a super powerful CPU, except it's got to talk to the application, and it's also running on another CPU in the same box. And every one of those calls across the Quick Path Interconnect and Intel boxes is roughly 20 nanoseconds in latency. You're paying real costs just for the fact that you didn't know that your threads are running on two different CPUs, and they need to know information about each other. So how are you going to manage all of that? So there are no visibility guarantees inside of the JVM explicitly. Whenever you're sitting there and writing multi-threaded code, you could update something with thread 1, and suppose thread 2 is entering into the same class into another method. It may not see any change that you're making. It is plausible. It might. How that happens, I'll describe to you a little bit later. But it's purely happenstance. Because in the JVM, we also have no low-level fidelity for how we deal with what's happening inside the physical machine. Right? It's all abstracted away from us. We don't see or talk to the low-level memory itself. So how do we deal with that? And worse yet, if we get to locking, and we say that we're going to have a lock that's going to protect this update to data, so only one thread can do it at a time. When they're not contended, performance is okay. But the second you have a contended lock, you are now all of a sudden dealing with extreme contention that has to be arbitrated outside of the JVM at the kernel. And so the threads that we're executing on core with all of their warmed cache data right there for them, both get pulled off. And the kernel figures out which one gets to go when, and then they have to get scheduled to another core, and all the data has to be reloaded from main memory, or maybe L3 possibly. That's an extreme cost, and that will hurt the performance of your application. So how many people feel really good about the difference between concurrency and parallelism? Okay. How many people saw the blog post that we wrote on the TypeSafe site about the case for message-driven? Awesome, I get to tell the story. All right, so, by the way, this is Joe Armstrong. He's the creator of the Erlang language, and he made the really pithy assertion, and he knows that this is pithy. He knows this is meant to just be a really simple way of diagramming it. The concurrent is 2 queues and 1 copy machine, where you've got to arbitrate who gets to go when, right? And parallel is, you've got 2 queues, but you've got 2 copy machines, so they're not coordinating at any point in time. They're isolated. They are, just like Mark was saying, completely split apart and have no points of, contention between them. Fantastic. My point is that the word concurrent isn't strong enough. It's concurrency and parallelism that you need to think about. Concurrent means things are happening at the same time. Concurrency means more like what needs to be arbitrated because it's shared. Right? So I like to wash dishes. I really do. I'm that crazy person who actually likes to wash dishes. Does anybody like to wash dishes?
Can you wash mine?
Yay, all right, woo. Yes, I will. I will wash your dishes. But finally, this happens at every meetup. One person says, yeah, me too. Do you also happen to like washing dishes and then putting them in the dishwasher? All right, woo, all right, me too. Well, I do scrub them, actually, because I'm just that silly. But the reason I do this is because I had a really terrible roommate in college who left crusty dishes and thought that the old dishwasher back then would just take care of things, and it doesn't. So, well, it didn't in the 80s, because I'm that old. Anyway, I have a process. I have dishes sitting on my sink. I need to rinse them off to get stuff off. I need to scrub them. I need to rinse them again, and then I'm going to put them in my dishwasher. I have a linear process. I have a synchronous flow of work, a pipeline, right? And that's fantastic, except I can't really make it much faster. What I could do is use locality to try and batch my tasks, because if I rinse all the dishes and then scrub all the dishes and then rinse all the dishes again and then put them all in the dishwasher, I can actually increase performance just by having locality to the faucet, to the scrubbing brush, whatever, right? But even then, I've got a process that cannot really be improved in speed. So you come over to my house and you say, I'd like to help you wash dishes. What's your name, by the way? George. So George is going to come over to my house and wash dishes with me, and I'm super excited about this, right? George shows up, and I say, here they go, please start washing dishes. I've now spawned work. I've got an asynchronous task, a thread of execution, George, who's now washing dishes for me. If I stand there behind him and I'm not doing anything, then I'm now blocking, right? I'm useless. He's probably getting mad. But, that's sort of how we operate in the old Java 7 kind of, threads with futures. They are a blocking API. And, it's still in Java 8 unless you use completable future, but neither here nor there. Well, I could do something else. I could go play with my kids. I could go watch TV. I'm not blocking, but I'm also not productive to a task, which isn't helping, because George is still a synchronous thread of execution who is not able to work any faster unless he's incredibly more efficient at dishwashing than me, and that's also possible. So what do? I go in and I help George. George is going to, take the dish, he's going to rinse it, he'll scrub. Then I'll take the dish, I'll rinse it, and I'll put it in the dishwasher. But now we have concurrency issues. First of all, I need to wait until a dish comes down the flow to me. And second, we have to arbitrate who gets to use the faucet at any given point in time. So we're kind of stuck. So what do? We say, well, let's increase the footprint. I'm going to go off to the bathroom and wash some of the dishes there. And that way, we can at least not have to arbitrate over faucets and stuff like that. But now I have a problem. I need to fork the work. I have to grab the dishes. I've got to figure out, do I just grab the top half? Or do I have to take one dish at a time? It's easy if I take the top half, because I have a fixed data set and I can just grab stuff. But that's not always how the real world works. Well, assuming I get the dishes, I go off and I go do my dishwashing, and George does his. Imagine we finish at the exact same time. And now we both come to the dishwasher, and we have to arbitrate who gets to put dishes into slots in the dishwasher. This is exactly how fork join pool works. You're forking work, You're joining at the end, and it may be more expensive than if you just used a simple array-based data structure with a really fast algorithm that, process the data on a single thread, believe it or not. Because fork and join are expensive because they're the coordination points. They're where concurrency is happening. So that's not ideal. Again, if I want to make this better, I have to increase my footprint even more. I have to find a way to broker the dishes between the two of us so that we're not figuring out who has to do what. Instead, it's figured out for us. The broker could be my kids bringing us dishes. Some go to George, some go to me. And then at the end, if I have another dishwasher, I've increased my footprint to have 2 dishwashers. Now I have no points of contention between George and I, and we can be faster and faster. And the more sinks, dishwashers, and threads I add, I'm linearly scalable. I can increase the performance of my application. So just in that analogy, we've talked about asynchronous, non-blocking, fork join, concurrency and parallelism, pipelines of work through streams. That's basically all it is, right? Is that any good to anybody like that? Okay. I hope it was. So I've been working on that for a while. So let's just think about what mutability means on the JVM. We have, and Rich Hickey talked about this, right? He had his whole talk about identity and value and state and time, right? I didn't want to reuse his names, but I really couldn't come up with anything better than the word value. If you look at the name, it's really the reference. It's the pointer to the data, right? We're not supposed to use the word pointer in Java, but pointers are everywhere in Java. They just didn't want anybody thinking about pointer math and pointer arithmetic, so they called them references. And on the right-hand side, we actually have the data that we're pointing to. When I say I've got a val, that just means it's final. I can't point to a new instance of a person. Once I assign it, I cannot look at any other place in memory. And on the right-hand side, hopefully, in this case, this is an immutable class. Let's just assume it is for now, that every value placed into it is immutable, right? In this case, I've got a first name and a last name. Those would have to be vals themselves. So how would this look kind of on the heap? This is a little bit wrong, but it's good enough for now. I've got my reference, me, pointing to an instance of a person which has 2 strings inside of it. The strings themselves are actually pointers to somewhere else in the heap. So, this is sort of the building blocks for how we get into things like structural sharing whenever it comes to collections. This is how your collections really look under the hood in Java and in Scala. And let's assume that this is a linked list. I've got an instance of a person, me. I've got another instance of a person, a friend named Jane Doe. And then I put us both into a list, right? And that's going to be a linked list. So I've got the reference for us, and it's immutable, pointing to a linked list element that has a pointer to the me and to the next cell, right? Because that's how cons together linked lists with cars and cooters work, right? And then my me is pointing to an instance of a person, which is pointers to the string instance of my Jamie and a string instance of my Alan. And the same thing goes for my friend. And they're scattered all over the Java heap, and they're moving because of the dynamics of generational garbage collection. They're going from the Eden new gen over to survivor spaces, over to old gen, and then there can be compaction phases which move them around trying to fit large items in somewhere else, right? So you don't have any guarantees that this data is anywhere close to each other. It might be just by happenstance, but that means that everything that's happening inside this list is a pointer chase. And what pointer chases mean is that the time an instruction is being executed on core, you're going to have a stall. You're going to have a point where your application, the execution of that instruction cannot happen because the data it needs has not been loaded in time. And that's when you get threads that are parked off to the side waiting for that data, all right? That's when hyperthreading comes really valuable because it says, all right, well, while this thing is waiting for data, I can have this other thing go and run in the meantime. Okay, well, if we had a value that was class scoped, then we would have to worry about locking, right? It's a field at the top level of a class. But if it's only inside of a method, it's pointer only lives inside of the frame of the stack of that method call, right? So you don't have to worry about concurrency in this case because nobody else except this thread, because it's a stack frame on a specific thread, can see this reference, right? That's nice. But don't take it for granted, because if somebody moves one thing inside of your application out of a method to the class level, now you have concurrency issues again, right? So just think about those kinds of dynamics. Now, we have the final keyword in Java, and that's really the basis for val. The great thing about Scala when Odersky was coming up with it was he made sure that you, at the time you were defining a variable, had to explicitly state whether this is mutable or immutable. You couldn't just forget a keyword, right? That's what we do in Java. I literally had a save action in my IDE when I was a Java coder, so I put final everywhere because, I wanted to make sure I didn't forget. But even that's infallible, or even that's fallible. So yeah, that's not enough. Final is only locking our reference to something, but what it's pointing to could still be mutable. Well, this leads to what I call the mutability matrix of pain. And let's assume that on the left-hand side here, we're talking about our name, the reference to the data in the heap. And we have a var, which is mutable, and a val, which is immutable, right? Fairly straightforward. And on top, we have the data it's pointing to. We have mutable state, which could be like a Java array list or a mutable list. There's no such thing as a mutable list in Scala. Mutable map, whatever, in Scala, that you can update in place. You can change the values inside that collection right there. And we also have immutable data that it's pointing to, like a case class or an immutable collection. What's inside of it cannot be changed without giving you a reference to a new collection. Well, if we have a var, which is something you can point to something else, and it's also the data it's pointing to can be changed, well, you're in for a world of hurt, like this kid putting a knife into an electric socket. That's a bad thing to do. It is totally not thread safe in any way, shape, or form. So you have to protect this in a multi-threaded world as much as possible. But you know what? Having a final pointer to mutable state is also crappy, because you don't have any guarantee that another thread isn't changing what you're looking at. And hopefully that's a crocodile. I was shooting for one. That means locking. Regardless of whether your name is final or not, you still have to make sure you're locking the mutable state in a multi-threaded environment. And that sucks. Remember that arbitration of contended locks? I'm talking about pulling threads off core and having them be arbitrated by the kernel. You don't want that. If we have a var, so I can point to different data, but the data it's always pointing to is immutable, well, then we're in a position of snapshots. And this is what we have when we have immutable collections that can change, all being, if I update that collection, I'm now pointing to a new instance, right? I can do that using a var. But I still have to worry about one thing, and that's the publishing of the new reference to other threads. Imagine, I've got one thread coming in, it changes what it's looking at because it's updated some sort of immutable collection. Now, if another thread's going to come in, it's got to make sure that it sees that I'm now looking in that different place rather than the old one. And the only way that's enforced is using the @volatile, or the volatile keyword in Java. So volatile is a memory barrier, a memory fence. At the time it is defined around a value, like my list that I'm creating, I'm saying that when this is update, stop what you're doing, make sure every other thread sees this change. It's expensive, but it's nowhere near as expensive as lock arbitration is. And if I am somehow able to stick in this val and immutable space, that's our happy place as far as thread safety goes, but it's not guaranteed. How can we have a program with effects whenever we don't change anything? The world's changing on us. It's hard to write purely immutable everything everywhere. So I like to stick here if I can, but then this is my next choice. And I never, ever want to go on that left-hand side. So there are implications to immutability. First of all, we are going to use more memory faster, right? And the thing about that means we've got a new generation of our garbage collecting, our heap, and we really can't influence how that is going to be collected because it's going to be stop the world. It is going to say the new generation filled up, and at this point, I've got to take the things that are surviving and move them over, wipe this clean, and start over. Okay, that's not much I can do about that. But if I made it larger because I'm using more of it, the impact of that is, well, I'm going to sweep up more stuff, and I'm going to mark more things, and it's going to take longer to perform the task. So believe it or not, increasing the size of new gen is not necessarily an option. That said, most people don't really run into this as a problem, even whenever they are using immutable data all over the place in Scala. I work with some of the largest customers in the world, banks, trading systems, pricing engines, fraud detection, you name it. And for the most part, it works just fine. It's only for people who have to work in the lowest latencies that are really worried about this. And whenever we get there, then we have to do some special tricks. So use snapshots anywhere you can, right? Avoid the train wreck that is things like locking. And by that I mean, make sure you use Volatile. But you have to use Volatile a specific way. Imagine I have that person class that I showed before, and I had the first name and I had the last name inside of it. Well, whenever I'm writing to it, maybe I have a method on it that says update name, and I pass in the first name and last name. I don't want to make both first name and last name fields inside the class Volatile, because that's a publish every time those are both updated. Update the first name, publish. Update the second name, or the last name, publish. Not what you want to do. Instead, if you can do it, make it so that you make the last name Volatile. And that way, whenever you update the first name, it's fine. Update the last name, now you publish as an aggregated update, right? If you're going to have any kind of mutable state or any kind of, snapshot-oriented data. And the flip side of that is you have to think of that as a write barrier, and then you're going to have a read barrier on the other side, where on the first read of, the last name should go first, because it's the one that had the volatile barrier on it. So when you're writing, do first name, last name. When you're reading, do last name, first name. So you guarantee thread visibility as much as possible, and consistency, right? So that's critical when you're using Volatile. There's a caveat. Just because you're using Volatile to publish doesn't mean that you won't incidentally see updates anyway. It's entirely plausible. Yeah, does anybody like these Robins? These cars are hilarious. The thing about Volatile that you have to know is, remember how I talked about all your data is on cache lines, and those cache lines are a certain size. They're 64 bytes in size. You can have multiple fields on a single cache line. Now imagine I say that I am going to change last name, and last name is on one cache line, and then there's a whole completely different field, some counter that is sharing that cache line with it. If I use Volatile, well, it's something that was using that counter could also see an update to the counter when it didn't need to. It's because the data is coming back as a group instead of a single field, right? So cache lines have to be in your memory. It's something you have to think about whenever you're dealing with this. If a value has to be seen independently, you may have to pad a cache line to make sure that other updates aren't somehow polluting whenever you have Volatile. Okay? Does that make any sense? Yeah. You've got multiple fields on a cache line. One of them is Volatile. You're going to see the updates to the other one whenever you try to, get an update to the Volatile field. That's just happenstance. But it does, it can be something that can mess with you. So use Volatile. By the way, anybody like the Fresh Prince of Bel-Air? Yeah, doing the Carlton? Yeah. Anyway, use Volatile and avoid locks as much as possible. And when you do this, you will have faster applications that are just as sane in a multi-threaded world. But when you do, think about the visibility guarantees and make sure you understand the dynamics of reads and write barriers. You can also get really, really crazy and deep with Sun-Misc Unsafe. But there be dragons. Don't just open that package unless you know what you're doing. It's not a free world down there. That's it. Any questions? Or? Yeah.
questions? All right.
So is there a reasonable analogous thing to like STM or
STM sucks.
TVARs or MVARs
STM sucks. I'm going to go out there and say this in a world where it's probably not, the thing that people want to hear. But STM is a live lock waiting to happen. If you have a certain number of fields and you have a certain number of updates, there's a mathematical certainty that you will at some point run into unable to commit, unable to commit, unable to commit, unable to commit. So, it's not deterministic. You can't even say that it's definitely at this time because it could be cache line location that causes it, distance to main memory. At some point, it will fall over. And so, in a world where I'm thinking about highly transactional systems, I can't use STM. That said, in a system where I don't have tremendous load, and I just want to make sure that somebody's first name and last name are updated at the same time, because I know that's not going to happen 5,000 times a second, STM's fine, right? I'm sorry, I cut you off.
That's all right. No, STM does have it's a transaction thing, right? And
Yeah.
Transaction can take an amount of time, and it can be blocked and then be forced to repeat. So yeah.
Yeah.
But MVARs.
I don't think I know enough about MVARs to make an assertion about that. So I'm gonna have to go look that up and get back to you. So yeah.
Oh, sorry.
I mean, I've heard the term, but I haven't read up on them enough.
So rather than diving into unsafe, is the contended stuff working now? The at contended?
So at contended was this idea that you could put an annotation onto a variable and say that it would not share a cache line. This was something Martin Thompson was getting really big on. I don't think they made it available to everybody. They made it a Sun-specific library, and they didn't even put it in unsafe, I don't think. And that really ticked off that whole mechanical sympathy crew. So, no, I don't think it's accessible to us. I'm not sure about that, but I'm pretty sure it's not accessible. But how great would that have been? Just put an annotation over a field and say that no other field can share the cache line with this, and therefore you never had to worry about things like that whole false sharing scenario I was talking about, where you don't really know what fields are on a cache line with you, and suddenly you could be hampered because what if both of those were somehow locked or volatile? And now, there's all this contention underneath your application that you're totally not aware of because of the happenstance that two fields that are unrelated are on the same cache line. That's the idea of false sharing. And at contended would have fixed it. They did create it. They didn't make it accessible to everybody, I think. And they have their reasons, like not making optional serializable. But they don't agree with it. Yeah.
So speaking of unsafe, so Oracle announced that it's going to get rid of unsafe. So, does TypeSafe have any good alternative to that? I mean, I guess that Play and Akka use unsafe, right?
They do use unsafe. Unsafe isn't really going away. They may make it more modular, which would be good actually, because right now you're opening this big Pandora's box with unsafe right now of all these different things that you could suddenly start playing with. Wouldn't it be great instead if you could just open up what you need, right? So that's what I think will happen. They haven't made their official decision yet. Am I correct in saying that? Anybody know for sure? They haven't decided yet. Yeah, but my guess is they're going to make it more modular.
Wait. Here you go.
Like talking about some of the various, like it's not going away like in 6 months, it's going away in a great number of years.
Yeah.
And there's already talks on, like arrays of structs and the various things you need to provide, most of which you went into unsafe for. So it's not like you just can't do that shit anymore. You won't be able to do that shit in 5 years once they've replaced most of it with better versions.
Yeah, and that would be great. Right now, Play and Akka rely on unsafe, but you know what? Anything low level does. Any of those high performance tools you see out there are unlocking unsafe and going in there. And even trying to unlock unsafe. Has anybody tried to do it? It's not easy. You got to look it up. You got to pull in a whole class of stuff that's going to unlock unsafe for you inside of your application. It's nutty. So it's non-trivial. And they won't mess with their entire ecosystem of performance nuts because that would really hurt the JVM, right? So, yeah, I don't see it. I don't see it end up being some sort of like, end of the world scenario.
Like we need some kind of modular effects system.
Yes, and you know what? Along that line, Odersky is researching it. He believes it too. There are some things that I don't think Odersky will ever do, like, pardon? No, a monad type. Yeah. Okay, I think it might be possible we get type classes as, again, I was telling Jed this, the future of Scala is going to change. The way Scala is going to be managed in the future is going to be changing. You're going to see Odersky taking less of a role in it. It's going to be much more community focused. That's all I can really say right now. But if you think of what that means, it could be messy. Let's be honest here. That if this becomes more community focused, the community is going to be arguing and trying to decide where this is going to go, and that's healthy. Let's all just keep our heads and try and find a way together to figure out the way forward for Scala. But it is going to change. So and this is a good thing, I think, for the entire community. Yes.
Sorry. When you were talking about mutable structures being bad, were you including concurrent structures, like the ones provided by the Java library or try map?
No, they're not bad. They're better than you locking your own structure, or locking around the access to your structure, things like concurrent hash map and stuff like that. But under the hood, they're still doing tricks that aren't free, trying to manage whether or not a thread can do what at what time, and whether that's at a compare and swap level, like atomic values and references. Varies from collection to collection. But, I mean, they're better. They're better than worrying about locks and stuff like that. But, they're not free.
So, if you have like a large collection, I was wondering if maybe that having the structure immutable with having to create a new one with all the objects maybe more costly. Or at that point, it makes more sense to use an external data structure?
The performance characteristics of Scala's collections are published. They don't talk about it in terms of at what size things go, bad. That said, if I have anything that's hashed and array-based, like vector, anything hash array map try-ish, then I'm fairly comfortable that the performance on, any operation except delete is going to be pretty good, right? Deletes are never pretty in general. So, does that answer it? Yeah, I don't know that anybody's benchmarked at what point performance starts to hurt. There was a really interesting, Christopher, did you see that thing that Victor passed out? Yeah, turn around. There was that presentation that was passed around about Scala collections and one other, it was like using JMH and stuff like that. Yeah, we got to share that somehow, because it was a really good presentation talking about various benchmarks being performed across, collections at size and the impact. So partially representing this, and maybe I can give this, I'll send it to Jed or something and he can share it with the group. Or I'll post it on the meetup page or something. Yeah.
I mean, you mentioned the general recommendation of immutable state stored within a volatile reference as your favorite of the two, but you also wrote a book on Akka, which is largely about messaging and serializing state, which kind of goes hand in hand with a local mutable because you're serializing at the message level. Don't those two things seem somewhat at odds?
No, not entirely. Yes, if you write Akka, if you write an actor and you don't think about the effects of the data inside of it possibly leaking, then yes.
If your data inside an actor is leaking, you're doing something pretty horrific.
Well, yeah, you're sending it out in a message. If it's a mutable state and you're sending it in a message, you're leaking it. So
yeah, but that's not even following the actor model at all.
Exactly.
So if
But it's enforced in Erlang. It's not enforced in the JVM because of the monolithic heap.
Yeah, but if we start talking at that level, we can just start setting nulls everywhere. So it's like we have to have some okay, well, any Scala reference you can send a null type system won't pick it up. We have to kind of expect people to follow the general principles at least slightly, or nothing on a JVM is ever going to work. So,
and that's why I don't see Akka as the kind of technology you use for the entire application you're building. That doesn't make sense whenever you want correctness, right? Because of the fact that you can't make any guarantees about messaging.
Sure.
So I'm a believer that you keep Akka at the boundary for multiple distributed applications talking to each other over messages. And then what's inside of the actors, inside of that boundary, is then purely functional.
Okay. I think there's something I'm not following, but it's not much use me dragging out here. I might.
Well, we can talk about it later. So, yeah.
Got a blog post on that one in case it helps. But anyway, I just wanted to, I didn't have a question, but I have a statement, and that is that Jamie actually did stay at my house the entire weekend, and he didn't do any dishes. I just wanted to.
Yeah, that's actually true. And you told your wife that I like to, and she didn't listen. She made you do them the whole time. Yes.
So you were talking about using Volatile, the memory fence from Volatile, to cover multiple fields.
Yeah.
How does that remain safe if those fields end up on different cache lines, so that the single memory fence won't synchronize that, will it?
Well, it's more about what the thread sees, what the thread is updated that needs to be published to other threads. It's not even the cache line affinity that matters, because what it's going to do is publish the changes it's made across all threads, which means it's going to sort of force the invalidation of variables that are exactly the same, that are on cache lines that are the same representation of cache lines in other cores and their cache pipeline. So, yeah, it's like a lower level dynamic than that.
That's kind of the point of the JMM. It says Volatile has this really kind of heavyweight kind of visibility guarantee.
Read and write guarantee, which,
absolutely everything that happened before that Volatile write and read is forced, right? And so it doesn't matter what your particular hardware is. That's the guarantee of the JMM.
And we have to have this for abstractions to work. If you think of something like Akka as an abstraction over concurrency, and mind you, that's not typically the reason I tend to use Akka. I like much more the fault tolerance thing. But if you think about it, I've got 20 messages inside of my mailbox. I have a thread that's given to me to handle 5 of them. And then I've got to give it up for the fairness that Mark was talking about. Mark wanted to make sure that I'm not starving other components in my system. So I handle 5 of them, and then I give my thread back. Then I get another thread from somebody that's completely different. That thread that I'm now given has to see the changes that were made by the previous thread in the same class. And they all have to be published to it. So while you didn't have to write the @volatile inside of your Akka class, it was done for you, so that the other thread given to you could then see the changes.
That's potentially actually a performance problem.
Yes. So, you cannot use Akka for high-frequency trading. It wouldn't make any sense.
And it's why things like atomics and compare and set, which give you weaker sort of visibility guarantees, give you much more specific ability to kind of reason about the performance guarantees if you're using multiple hardware.
But know what you're doing. Yeah. Right? And that's where the HFT folks are, right? And the people doing that are extremely low-level oriented and really good. At the same time, you know what? They don't know what happens whenever a thread fails in Java either, because nobody writes uncaught exception handler. Mark talked about using multiple thread pools for isolation. Really, thread pools in that world should be a domain object. They should be. You should be saying that the only things happening on a thread in this thread pool is customer updates in the database. That way you can have in your uncaught exception handler behavior specific to failure for updating customers. Because if you make it something across all these other domain types, oh my God, you'll never be able to reason about failure inside of your application. Or get this, compose it. Composing failure is possible now. Failure is nothing more than messages. And now you have the ability to say something happened over there, something happened over here. What do I do about it in the aggregate? How cool is that? It's not the same kind of failure as flat map, or not failure. Not the same composition. It's not the same kind of composition as flat map, but it is a meaningful form of composing failure across multiple places in your system. And you can do it with thread pools if you know what you're doing. It's hard. You still have to have a messaging layer. Yeah, Angus, you have a question?
So before you were talking a bit, I guess, about locality of reference, and I could be displaying my naivety here to the JVM, but do you feel that lack of value types is a kind of sore point for this?
Well, okay, I don't know how much value types are actually going to have to do with... they are going to actually... Okay, value types in the JVM are going to change the fact that you aren't going to be looking one more level deeper at a pointer.
Yep.
That's good. But physical representation in a linked list is still going to be pointer chasing. So you will be able to use non-array backed structures that are contiguous in memory for locality of primitives now, and that is exciting.
When you say now, what does
Not now, I mean whenever Valhalla is done, which is actually Java 10.
Right.
Is that right? Java 10? Yeah, okay.
Okay. So I mean,
we don't even have a date for Java 10 yet, so
yeah.
Yeah, it's a while.
So like I've got an instance of something at the moment that like sorts, I don't know, 2 million rows or some crap into maybe 12.
Okay.
And it's stuck into array because locality of reference, but because those instances could be from anywhere in this gigantic collection, you sort of, like once you go beyond one level of indirection, everything falls out the window.
Yeah.
Yeah, which sucks.
It does. I hope it gets better.
Cool.
You know, and it's funny because everybody knows that Scala had an attempt at specialization that didn't really go so well. You know, it was a valid attempt in a PhD research thesis, but, you know, it's not something you would want to use in the real world. And, you know, the Oracle team, like Brian Getz, have been coming to us and talking to us about what we learned trying to do it, because now they're going to have to do a whole bunch of specialization on their own Valhalla implementation. We'll see how that goes. At least they've got the money to throw at the problem. This was, you know, PhD students. It's a market difference. So hopefully they do it right. Does anybody care about Java 9? Anybody care about Java 9? Anyone? Just asking.
In theory.
In theory. Literally nobody cares about Java 9 right now. It's
Care about what might happen to the JVM.
why? What is...
Possible improvements.
Yeah, okay. Possible improvements on the JVM? Like what?
I haven't looked at that yet, but
Okay. I mean, like, if you talked to Doug Lee and you told him that you were still running Java 6 when Java 7 was out, he would have a conniption fit just because of all the improvements he sees between 6 and 7. But most people were like, 7 is irrelevant to me, I don't care, right? But to Doug Lee and somebody who's really worried about what you're seeing performance-wise and in concurrency world, you know, it was a really big release. Java 9 has the same kind of potential. You know, nobody's going to care because it doesn't have anything flashy inside of it. But oh well, you know, I don't know. It's going to be interesting to watch whether people adopt Java 9 at all.
But 7's like advantages were
Fork join.
Yeah, but they were still, for even something written well, was still only in the, you know, sort of 20%.
Yeah, nobody was using invoke dynamic, that's for sure. Which one? It could have. I don't remember that.
It did. There was something substantive. I mean, it's been a while.
Could be why Doug was flipping out when nobody was adopting it.
But there was something that was like 30 to 40% on primitive arrays, I believe.
Array copy. Was it array copy?
I think it was even more general than that. I think it was just the memory layout of arrays of primitives. But
possibly.
I could be wrong, but it was something big. And it was definitely collections.
Which would matter for strings?
Broken options, right?
What?
I know a lot of people probably want to like take off, but I'm open to answering any kind of questions you want, by the way. I mean, it doesn't have to be about my talk or anything. So Feel free to fire away.
So guilty.
Sorry.
Guiltinay, yeah. Yeah.
He was here a while back, and he was suggesting a mechanism that he might be able to get localized array structures into Java via, I think, what do you call it, Objet Layout?
Yes.
As a thing. And then trying to get that into the spec so that then the authors of Hotspot, etc., could use it and whatnot.
Yeah.
Do you know if that's got any chance of getting into the spec?
The mechanical sympathy crew, for whatever reason, has really annoyed the Java language stewards like Brian Getz. John Rose. I don't know how or why, but that whole object layout thing, for all the talk on mechanical sympathy mailing lists and stuff like that, I've heard nothing about it from Oracle. Is anybody? So this could be an uphill battle. The crazy thing about this is Gil could throw this into Zing and probably, really benefit from the performance gains he gets. But he's trying to make it standardized across all JVMs. Other things about Gil, by the way, if you ever want to know how to measure latency, like Mark is sitting there talking about across multiple percentiles and multiple throughputs, see his talk about this. Did he do that here? Yeah, isn't that great? And his tool, WRK2, check it out. It's the one doing its histogramming of all of your information at various throughputs. Totally worth checking out for doing your volume testing. WRK2. But yeah, he's amazing, isn't he? He will sit and talk to you for hours about stuff. He's just the nicest guy. Yeah. All right. Oh, by the way, there's stickers in the back. If anybody didn't see that, please help yourself. Yeah.
Will the Scala library get smaller in size?
Will the what?
The Scala library get smaller in size?
I don't know. Will the Scala library get smaller in size? I'm not going to say yes to that. I'm going to say probably not. And as an Android developer or a JavaScript developer, maybe Scala.js will finally force our hand. Right now, it's not a priority. Because most of the people who are using Scala are on the server side, and, memory's cheap in that world. So yeah, I would say no. And you know what? Christopher over there is doing some really interesting stuff about shared libraries, trying to share libraries across multiple JVM deployments. Or no, in a single JVM, right? Almost like, no, not in a single JVM, multiple JVMs. Multiple JVMs. Yeah, we were talking about this weekend. So
that matters to us. We've had multiple times where, you add the Scala libraries, and even on the same node in a cloud deployment, every single JVM, it increases the memory footprint of each one, even though it's the same thing being loaded up multiple times. So if you can just share that, and there's multiple reasons. It's really boring, but
Christopher's trying to make the case internally right now for it.
Yeah.
So
awesome.
Yeah, certainly talk to him.
Yeah. All right. Okay. I think we're done. Awesome. Jamie, thanks for coming.